This video provides an introduction to our work, titled Point-Level Visual Affordance Guided Retrieval and Adaptation for Cluttered Garments Manipulation. Manipulating piled garments poses significant challenges. Garments, as a type of deformable object, differ greatly from rigid objects due to their high-dimensional state spaces and complex kinematics and dynamics. While most studies focus on single garment manipulation, real-life scenarios often involve multiple cluttered garments, such as arranging clothes on a bed or retrieving items from a washing machine. These scenarios are far more challenging because of the intricate states and interrelations between garments. In addition, garment piles often present multiple plausible retrieval targets, which increases the demands on the policy's representation and decision-making capabilities. Existing large foundation models struggle to effectively select suitable manipulation points in these scenarios. For example, we tried using the Segment Anything model to segment the outline of each garment and identify the most suitable manipulation point by analyzing the center points of the segmented areas. However, as shown in this segment result image, the model fails to accurately segment piled garments, making it impossible to determine appropriate manipulation points. We also explored using ChatGPT-4o to infer potential spatial relationships between garments using RGB and depth images. Unfortunately, the performance was far below expectations. The model seems to just select random points, which were unreasonable in most cases and unsuitable for effective manipulation. To address these issues, we developed a solution centered on affordance. Our project makes several key contributions. Firstly, we propose to study the novel task of cluttered garments manipulation and build the pioneering environment, including scenarios like retrieving clothes out of the washing machine, arranging clothes on the sofa, and taking clothes out of the dirty clothes basket. Secondly, to solve such tasks, we introduce point-level affordance, which represents the per-point actionability on the object for downstream tasks, with multiple novel designs to efficiently represent highly complex state and action spaces, and multi-modal policy outputs. Meanwhile, we empower point-level affordance with the awareness of garment structure and relations, respectively preventing the target garment from contacting the floor and dragging out other garments during retrieval, which are the two main failure scenarios in our task. For highly tangled garments with few plausible manipulation points, we further develop the adaptation module guided by learned affordance, which can reorganize the scene and thus garments plausible for manipulation will exist. This part is about the overview of our framework. Given the observed point cloud, the affordance module predicts the initial point-level retrieval affordance score. When actionability is not good enough, the framework proposes the adaptation pick-place action. It first predicts per-point pick affordance, and selects the pick point with the highest score, conditioned on which it predicts place affordance and selects the place point. After executing adaptation action, it receives a new point cloud and generates new affordance. When actionability is good enough, the robot retrieves on the point with the highest affordance score. This loop is executed until all garments are retrieved. Here are the details of the learning framework of retrieval, pick and place affordance. First, we train the affordance module, which predicts the point level, retrieval, affordance score for the downstream task. Taking as input the point cloud observation O of the garment clutter, we extract the per-point feature using PointNet++. We follow 3 points A, B, C in the point cloud, and we can find that for A, which is unaware of the garment structure and has a low score, leads to an unsafe retrieval. For B, the robot retrieves the target garment safely and cleanly, and for C, which is unaware of the interrelation between garments, leads to an unclean retrieval. The PointNet++ backbone within the module aggregates both local and global features that facilitate incorporating garment geometry, structure, and relation information for each point. Next, we train the place module, which predicts the point-level place score conditioned on a pick point for adaptation and is supervised by the trained affordance module. We use one PointNet++ to extract the feature of the given pick point, and another PointNet++ to extract features for place points. Then their feature concatenation is parsed into MLPs to predict the place affordance. We follow 2 points A, B in the point cloud, and we can find that for A, which has a higher score, leads to a better retrieval affordance. For B, which has a lower score, leads to a worse retrieval affordance. Finally, we train the pick module, which predicts the point-level place score for adaptation, is supervised by the place module. We follow 2 points A, B, and we can find that A leads to a bad place affordance, while B leads to a better place affordance. We tested our framework in simulations using a Franca Panda arm, 9 categories of garments from CloseKnit, and 3 realistic scenarios: a sofa, a laundry basket, and a washing machine. In the sofa scenario, the top row of images demonstrates the step-by-step retrieval process, while the bottom row shows the corresponding observations and affordance details. For the laundry basket scenario, where garments are more severely tangled, the retrieval process involves 2 adaptation steps. The bottom row highlights 1 adaptation step and 1 retrieval action. In the washing machine scenario, a video shows the complete retrieval process, including the corresponding observations and affordance details at each step. In the real-world setup, we used a Franca Panda arm, 5 different types of garments, and a Kinect camera across 3 scenarios. For the washing machine and sofa scenarios, we demonstrate how the model uses pick and place affordance to improve retrieval efficiency. For the washing machine scenario, we show a video of the whole process. At each step, we show the corresponding observation and affordance on the left. For the other 2 scenes, we also show the videos of the whole process to demonstrate the effectiveness of our method. That's all about our work. Thanks for your listening.